Hello everyone and welcome back to the channel. It's been a while since my last video. In today's video, we're going to take a look at a small but very useful module that many makers and embedded developers have probably come across at some point, the ADS1115. In this video, I'll walk you through the basics of using the ADS1115, show you how to connect it to an ESP32, and demonstrate how to read analog input values through the I2C interface. As always, I'll try to keep everything simple and practical, so even if you're new to this module, you should be able to follow along without any trouble. So, let's get started. This is a 16-bit ADS1115 module that I bought from AliExpress for a pretty low price. The module communicates through the I2C interface, which makes wiring and integration quite simple. You can select the I2C address using the ADDR pin, allowing up to 4 different I2C addresses. This means you can connect up to 4 ADS1115 modules on the same I2C bus if you need more analog inputs. Each module provides 4 16-bit ADC input channels, labeled A0 through A3, which can be used to measure analog signals from a variety of sensors and devices. To make things a bit more practical, I designed a small PCB for the ADS1115 module some time ago. On this board, I added a jumper that allows you to select a common operating voltage of either 3.3 volt or 5 volt. I also included a dip switch block for selecting the I2C address. Instead of rewiring the ADDR pin, for this demonstration, I'll be using a standard 10K potentiometer to test the ADC input channels and verify that everything is working correctly. In this video, I'll be using a custom PCB that integrates an ESP32-C3 SuperMini and an OLED display to read and display analog input values from the ADS1115 module. The custom PCBs shown in this video are open source and have already been shared on my GitHub. If you're interested, you can visit my GitHub page, find the repository called Some Custom PCB, and download the complete schematic files, PCB layouts, and example source code. I've included all the relevant links in the video description below for easy access. In this section, I'll show you the basic wiring between the ADS1115 and the ESP32-C3 SuperMini. First, connect the VDD pin of the ADS1115 module to either 5 volt or 3.3 volt from the ESP32, depending on your setup. Next, connect the GND pin of the module to the GND of the ESP32. For the I2C interface, connect SCL to GPIO6 and SDA to GPIO5 on the ESP32-C3. We also need to select the I2C address using the ADDR pin. I've included an address reference table on the screen for convenience. When the ADDR pin is connected to GND, the module uses address 0x48. Connecting ADDR to VDD changes the address to 0x49. Similarly, connecting ADDR to SDA sets the address to 0x4A, while connecting it to SCL sets the address to 0x4B. This gives us a total of 4 available I2C addresses, allowing multiple ADS1115 modules to share the same I2C bus. By default, the ADS1115 uses the I2C address 0x48. which means the ADDR pin is connected to GND. If you're only using a single module, you can leave it as is. I'm only showing the address selection here for demonstration purposes. The pins A0 through A3 are the analog input channels. You can connect a potentiometer for testing or use various analog sensors such as NTC thermistors and other analog output devices. One important thing to note is that the analog input voltage must stay within the limits specified in the datasheet. The maximum input voltage should not exceed 6.1 volts. So if you're working with signals such as 0, 10V, do not connect them directly to the ADS1115, as this may damage the module. In that case, you'll need additional circuitry such as a voltage divider to reduce the input voltage to a safe level. During my testing, I discovered an issue when connecting the ADDR pin to SCL to select the I2C address. According to the datasheet, tying ADDR to SCL should set the device address to 0x4B. However, in my tests, the module consistently failed to respond at that address, and the I2C scanner could not detect the device. I'm not sure whether this is a limitation of the particular module I purchased or an implementation issue, but it's something worth keeping in mind. Because of that, I recommend using the other 3 addresses, which worked reliably during my testing. Personally, I would avoid connecting the ADDR pin to SCL unless you've verified that it works correctly with your specific module. As for the alert pin, it is an open drain output that can be used to indicate different events, such as successful data conversion or error conditions. For a simple test, you can connect an LED to this pin. Connect the cathode of the LED through a 1K resistor to VCC, and connect the anode to the alert pin of the module. Since the alert pin is open drain, it works by pulling the signal low when active, making this wiring method suitable for basic status indication. With that, the hardware wiring is complete, and we can move on to the next part of the project. Now we come to the final part of the video, which is also one of the most important sections. We'll write a simple program to communicate with the ADS1115 module and read analog values from its input channels. To keep things easy to understand, I'll be using an existing library together with the datasheet. This approach allows us to get started quickly while still understanding what's happening behind the scenes. The library I'm using in this video is designed for the Arduino framework. Even though it has been around for nearly 10 years, it's still well-maintained, feature-rich, and very easy to use. Back in VS Code, the first thing we need to do is install the ADS1115 library into the IDE. I've already made a video showing how to install libraries in VS Code and PlatformIO, and you'll find the link in the video description. Now let's start coding. First, I'll create an instance of the ADS1115 class and name it ADC0. You can use any name you like, but I prefer ADC0 since it makes the code easier to read when working with multiple ADC modules. We need to define the I2C address of the ADS1115 module. We already covered the available addresses earlier in this video, so I'll be using the default address, which corresponds to the ADDR pin connected to GND. Next, I'll create a separate function to initialize and configure everything related to the ADS1115 module. I'll name this function Init ADS1115. The purpose of this function is to keep all ADS1115 setup code in one place, making the project easier to read and maintain later. Whenever we want to use a feature provided by the library, we simply use the ADC0 object that we created earlier, followed by the function we want to call. For example, here I'm calling the initialize function to initialize the ADS1115 and establish communication with the module before we start reading any analog values. Okay, let's quickly look at the datasheet. For the ADS1115, there are 4 main settings you need to know. Input multiplexer selects which analog input to read. PGA, programmable gain amplifier, sets the input voltage range. Operation mode, choose continuous or single-shot mode. Data rate, controls how fast the ADC converts. The most important one is the PGA. The ADS1115 supports input ranges from 0.256 volt to 6.144 volt. For example, in this video, the maximum voltage coming from my potentiometer is 3.3 volts, so I'll select a PGA range of 4.096 volts. If your analog input can reach 5 volts, then you should select 6.144 volts instead. In general, always pick a PGA range a little higher than your maximum input voltage so the ADC can read the full signal correctly. Of course, the ADS1115 has more features than I'm covering here, but for this video I'll keep it simple and focus only on the settings needed to get it working quickly. Now let's go back to the code. First, I'll set the operating mode with the set mode function and choose ADS1115 single-shot mode. This means the ADC only takes a reading when needed, which helps save power. Next, I'll set the data rate. The ADS1115 can go up to 860 samples per second, but for this example I'll use 32 SPS, since that's enough for a potentiometer and other slow-changing sensors. To do that, I'll use the set rate function and select the desired conversion rate. Next, I'll configure the programmable gain amplifier, or PGA. Since the maximum input voltage in this setup is 3.3 volts, I'll select a PGA range of 4.096 volts. To configure the PGA, simply call the setGain function and select the 4.096V range. I also want to use the alert pin that we connected to an LED earlier. This will allow us to visually monitor conversion events and quickly identify whether the module is operating correctly. To enable this feature, I'll use the setConversionReady pin mode function. Now let's move on to the void setup function. First, we need to initialize the serial monitor and set the baud rate to 115,200. This allows us to print ADC readings and debug information. Next, initialize the I2C bus using the wire library. Finally, don't forget to call the Init ADS1115 function that we created earlier. This ensures all ADS1115 settings are applied before the program starts reading data from the module. Now let's move on to the loop function, where we continuously read data from the ADS1115 inputs. First, we need to set the input multiplexer for each channel. In this example, all 4 channels are read separately without differential mode. For channel A0, we call setMultiplexer and select P0NG, which tells the ADS1115 to measure A0 relative to ground. Then we call triggerConversion to start the ADC conversion. Since the alert pin is enabled, it will briefly go low when the conversion finishes. The LED will blink continuously, showing that the module is working. After the conversion is done, we use getConversion to read the result and store it in raw 0. The other channels work the same way, with only the multiplexer setting changing. P1NG for A1, P2NG for A2, and P3NG for A3. The results are stored in raw 1, raw 2, and raw 3, giving us the raw 16-bit ADC values from all 4 channels. At this point, all we need to do is print the raw values we read earlier to the serial monitor so we can view the ADC readings from each input channel. To make the output easier to read, I'll add a delay of about 1 second between updates. This gives us enough time to observe the values without the serial monitor scrolling too quickly. Now I'll build the project and upload the firmware to the ESP32. Once the upload is complete, we can open the serial monitor to check the results. I prefer to place it in a separate window so it's easier to follow the incoming data. As you can see, when I rotate the potentiometer, the ADC values update continuously and respond smoothly to the input changes. The readings are also very stable, with very little fluctuation or noise, which is one of the main advantages of using the ADS1115 compared to many built-in microcontroller ADCs. Alright, that brings us to the end of this video. Today, I showed you how to use the 16-bit ADS1115 module to read analog signals through the I2C interface. It's a simple and effective solution for projects that require more accurate ADC measurements without adding a lot of extra wiring. I've shared the complete source code on my GitHub. The link is in the description below, including the OLED display example used in this video, so feel free to download it and use it as a starting point for your own projects. If you found this video helpful, don't forget to leave a like, subscribe to the channel, and share it with others who might find it useful. Thanks for watching, and I'll see you in the next video. Good luck with your projects.